This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Hi everyone, welcome to Physics 1, Lecture 9. Today we are going to focus our lecture on energy. More specifically, we're going to focus on kinetic energy, work, and power. You'll remember from our previous lecture that we looked at examples of forces. We looked at things falling from a height, what kind of injury we might face if we jumped off a building, how airbags can save lives, and how we actually perceive weight, which isn't how it actually works, but how we perceive it because of our perception mechanism in our inner ear. We also had a look at uniform circular motion and dead centripetal force. So today we're going to focus on energy, and you'll probably recall from high school or earlier physics courses, there's two general types of energy. There's kinetic energy and there's potential energy. Well, for any kind of motion, it's going to require energy, whether it's atoms moving or the universe expanding or shrinking, it's going to require energy. So energy is a scalar quantity that is assigned to an object or a system of objects. It can be changed from one form to another. We'll discuss this further in this lecture and the next lecture, but you'll remember from previous physics courses how you can transfer kinetic energy to potential energy and vice versa. It is always conserved. Energy is always conserved in a closed system. That means that the total amount of energy of all types is always the same. As Einstein said, energy is neither created nor destroyed, but simply transferred from one form to another. So in this chapter, we're simply going to focus on kinetic energy, or the energy of motion. We're also going to discuss one method of transferring energy, which is work. So kinetic energy, the energy of motion. The faster an object moves, the more kinetic energy it has. Kinetic energy is zero for a stationary object. If you just remember kinetic being motion, if it's not moving, there's zero kinetic energy. So for objects with a velocity, this is for all objects well below the speed of light. Of course, when we start to get velocities near the speed of light, things change, and that's when we have to utilize special relativity. But right now, we're working in the normal, everyday world. For an object with velocity, we can write the equation as k is equal to 1/2 mv squared, where k is the kinetic energy, m is the mass, and v is the velocity. The unit of kinetic energy is a joule. A joule, the breakdown SI units is 1 kilogram meters squared per second squared. So what are some examples? Kinetic, let's go back to our kinematic equations and try to conceptualize this mathematically. Energy released by two colliding trains, each with the same weight and acceleration from rest. So what you're looking at is a set track, two trains on either end, they accelerate towards each other until they crash. What is their combined energy at impact? It's a very sort of violent and macabre sort of question, but let's have a go with it. So we need to find the final kinetic energy, the final velocity of each locomotive. So what we can do is we can go back to our kinematic equations, the one that we used quite a bit in the last lecture as well. This is our final velocity with respect to position. So we look at our initial velocity, which in this case is 0, because both trains are starting from rest. And it's 2a, and that change in position. So they've given us some information. We know the acceleration is 0.26 meters per second squared. And we know the total length of the track is 6.4 kilometers. And the weight of each train is 1.2 million newtons. So when we just have to think about this carefully, because so there's one track that's 6.4 kilometers long, and the trains on either side accelerating at the same rate towards the center. So what that means is for each train, that distance is going to be half of the total track. So we can take our equation, we simply plug it in, plug and chug. Our initial velocity, of course, is 0, 2 times the acceleration, which is given to us, and 3.2 times 10 to the third meters. That's half of that distance. That's half of that. It's 3.2 kilometers. So when we plug our numbers in, we actually find out that the result is 40.8 meters per second squared, or about 147 kilometers an hour. So imagine 2 trains at that weight impacting, and both of them have a velocity of 147, traveling at 147 kilometers an hour. That's pretty significant. So what we need to do now is see the total energy. We need to know what the mass is. Now, it gave you the weight, but the weight is different from the mass. The weight is mg. The mass is simply m. So what do? We take the number they've given us, which is in newtons, because it's force, it's the weight. We simply divide by g. We find that it's 1.22 times 10 to the 5th kilograms. So that's actually 122,000 kilograms each train. So if we use the equation of kinetic energy is 1/2 mv squared, and we're going to add them for each train, and because for each train the kinetic energy is the same, we can simply multiply it by 2. So it's 2 times 1/2 mv squared. So the 1/2 comes out. We just look at the mass times the velocity squared. And what we get here is 2 times 10 to the 8 joules. That's 200 million joules. That's a tremendous amount of energy. So let's account for changes in kinetic energy by saying energy has been transferred to or from an object. Anytime you transfer energy through a force, you do work. Now remember from before we talked about work. Work is equal to force times distance. In this case, we're looking at any kind of force that involves a change in energy, which pretty much is all force is. So work is done on the object by the force. So work energy is transferred to or from an object by means of a force acting on the object. Energy transferred to the object is positive work. Energy transferred from the object is negative work. So to the object, positive, from the object, negative. It's not really the common meaning we use the word work, but that's all right. So to do work on an object, energy must be transferred. If we throw a baseball or throw a cricket ball, because we're not in the States, if we throw a cricket ball, we do work. But if we're pushing against something that is immovable, like if I'm pushing against a wall but it's not moving, I'm not doing any work. It has to move. There has to be a displacement in order to be doing work. So let's start from our force equation and do a little bit of derivation here. Let's try to figure this out. So just looking in one direction, let's look in the x direction. Force is equal to ma. We've been over this many times. And we use our kinetic equation that we used before in the previous question, our velocity with respect to position. And that's our final velocity squared is going to be equal to our initial velocity squared plus 2, the acceleration times the acceleration in the x direction times whatever that distance happens to be. When I derived those equations initially in free fall, things going up and down were in the y direction, so I simply used height. Yesterday we used final position minus initial position for x. It doesn't matter, it's just that change in distance for that equation. So we can now rearrange this into kinetic energies. So 1/2 mv squared for the final velocity minus 1/2 mv squared for the initial velocity is equal to our force times our distance. Now remember, there's an acceleration component in that, which is in the kinematic equation. So again, you should always have a tablet or a piece of paper with a pen and be working through these equations and through the mathematics as we're going through the lectures. So you can see the two equations here. We can plug them in. We now see the left side is now the change in energy. So we've got the change in the energy from final velocity and initial velocity that's going to equal force times our distance, which is our work. So to calculate the work a force does on an object as the object moves through some displacement, we use only the force component along the object's displacement. The force component perpendicular to the displacement does zero work. What I mean is if we push something, if we take a force on something, it only moves in one direction. That's all that matters. That's what we're looking for, that force component. This does work. This part doesn't do work because there's no displacement in that direction. So if we move something, doesn't matter what it is, how we're adding force to it, if it only moves in one direction, then the work is being done in that direction. Work is not being done perpendicular directions, up or in, for example. For an angle between the force and the displacement, we simply go back and we use the same vector quantities that we've been using all semester so far. So just for these equations, they are simplified. We're looking at a constant force. The object is like a particle, it's rigid, and the work can be positive or negative. So let's have a look here. What we have is we have a wire and there's a bead on that wire. So the bead can only go along the wire. We'll just say that's the x direction. So I can take a string and tie it to the bead. Doesn't matter how I pull it, it's only going to be able to move in the positive or negative x direction, which means the component of the work is in that x direction. The y direction or the z direction, there is no work. So if we add more kinetic energy to it, it's going to be going faster. That's simply because of the equation. We can see that already. Now remember that the units for work, the SI units for work, are joules. They're exactly the same as energy because remember, work is just a transfer of energy. So a force does positive work when it has a vector component in the same direction as the displacement. It does negative work when it has a vector component in the opposite direction. It does zero work when it has no such vector component. That's just summarizing what I said a second ago. For two or more forces, the net work is the sum of the forces done by all the individual forces. This is the same as we've done before. The net is just the sum of everything together, all the different components. We can utilize two methods to calculate net work. We can find all the works and sum individual work terms, or we can take the vector sum of all the forces and calculate the net work once. So what is the work kinetic energy theorem? The work kinetic energy theorem is that the change in kinetic energy between its initial state and its final state is work. We're going to say this over and over and over again so everybody gets it. The change in kinetic energy is the net work being done. So we can write the final kinetic energy as the initial kinetic energy plus the work. You can move it around algebraically. So the work kinetic energy theorem holds for positive and negative work. So let's do an example. If the kinetic energy of a particle is initially 5 joules, and we transfer 2 joules to the particle, so it's doing positive work, you're simply adding those two, you're going to get 7 joules. If the net transfer is from the particle, it's negative, it's taking away, you're doing negative work, then it's 5 joules minus 2 joules, which is 3 joules. So we calculate the work as we would for any other force. So we use our same equation. The work for gravity, for example, is equal to weight, that's the force, mg, ma, weight, times the distance. In this case, distance cosine of phi. So this is the dot product, or the scalar product, which we did the first week of the semester. So if we're lifting an object up for a rising object, that work, the cosine is going to be 180 degrees, which is -1. So therefore it's minus mg times that distance. For a falling object, the cosine is going to be 0, which is positive 1. So it's mgd, or positive mg times that distance. So work done on lifting or lowering an object, we can apply an upwards force. What we have is the change in kinetic energy, the final kinetic energy minus the initial kinetic energy, is equal to the work of the acceleration plus the work of gravity. And that's just going back to the previous page again. So we're lifting something up. So we've got the work of the gravity pulling down on it, and we've got us actually letting it drop down, that work as well. So we're lifting an object or lowering it, it's going to have slightly different meanings. So for a stationary object, the kinetic energy is 0. Therefore, WA plus WG is equal to 0. Therefore, we can see that WA is equal to minus WG. Simply the sum of the energies. So in other words, for an applied lifting force, WA, this is the work done in lifting or lowering something, is simply equal to minus mg times d cosine of theta. That's the same thing as saying force times distance. And this applies regardless of the path. So we're going to look at a couple of different examples here. So figure 7.7 shows the orientation of forces and their associated works for upward and downward displacement. So we've got a force that does positive work going up and a force pulling back down that is negative. But the overall displacement in this case is going up. Or in the case below that, if the displacement is going downward, the force component in that direction is positive, and the force direction opposite that is negative. So in the first case, as if I'm lifting something up, gravity is negative because the displacement is positive. In the second one, where it's falling down, going downward, that displacement towards down means that the force of gravity is positive, and the other force is negative. So you'll notice that the works in equation 7.16 need not be equal. They're only equal if the initial and final energies are equal. So it's going back here in 7.16. They're only equal, the works are only equal if the kinetic energies. The final and the initial kinetic energies are equal. If the works are unequal, you'll need to know the difference between the initial and the final kinetic energy to be able to figure out the work, to solve for work. So let's just have another conceptual question here. Example, your passenger being pulled up a ski slope. I guess that's Rudolph pulling Santa up a sleigh. Bizarre questions they give in this textbook. So because you're being pulled up the ski slope, we remember from our free body diagram that in this case, we're sitting on the ledge, on the slope. We've got the normal force going above us, outward away from that perpendicular to where we're sitting on the slope. We've got mg cosine theta going down. We've got the force of gravity pulling us down towards the earth, and the tension is going upwards. So in this case, the tension does positive work and gravity does negative work because we're being pulled up the ski slope. However, if we're in a lift or an elevator and we're being lowered, the tension does negative work and gravity does positive work because we're going down. So it's just reiterating what I said a couple of slides ago. So now let's have a look at work and Hooke's law. So Hooke's law relates to spring forces. So all of us have seen a spring. A spring force is the variable force of a spring itself. It has a particular mathematical form, and many forces in nature have a similar type of form. So looking at figure 7.10, in the top one, A, you're seeing it in a relaxed state. So you've got a wall with the spring attached to it, and the other end of that spring, you've got a block. So if I'm pulling the block out, if I'm extending the spring, the force is going to be pointing back towards the spring itself, back towards the wall. If I'm pushing the spring inwards, it wants to resist that going the other way, so it's pushing out against my hand. So we can stretch or extend the spring, it's going to resist, and that exerts a restoring force. What force does it need to get back to where it's in its rest position? It wants to be in that relaxed state. So the relaxed state is where it's neither compressed nor extended. So the spring force is given by Hooke's law. And Hooke's law is that the force of the spring is equal to negative k times the distance. The negative sign represents that the force is always opposite of the displacement. So again, when I push it, the force is going away of the displacement. If I'm pulling it out, the force is going inward. That's where the negative sign comes from. The spring constant is K. It's a measure of the stiffness of the spring. So a real heavy, rigid spring is going to have a much higher value for K than a real thin, more flexible, easier to move spring. So this is a variable force, which means it is a function of the position, and it exhibits a linear relationship between the force and the distance. So for a spring along an x-axis, one-dimensional, we can simply say the force in the x direction is equal to minus kx. So what is the work? Remember that work is equal to force times distance. So in this case, we can say that work is equal to force times that infinitesimal increment in distance. We're going to utilize the theorem for calculus here, which means that work is the integral of the negative value of force times distance. So for the force, using Hooke's law, we know that it's minus kx. So we plug minus kx into that equation, the negative signs cancel out, and then we take the integral of that value with respect to the position. And of course, the integral of x is going to be x squared over 2. And then we just see here that the work is the change in the kinetic energy, or the change in Hooke's law. It can be positive or it can be negative, and it's going to depend on the net energy transfer. So what we've done here is we've simply done a very easy and simple derivation of the work with respect to Hooke's law. So just reiterating, work is positive if the block ends up closer to the relaxed position, x equals 0, than it was initially. It is negative if the block ends up farther away from the x position, like x equals 0. It is 0 if the block ends up at the same distance from x. So, we just draw this on a piece of paper, work this out. It's actually not terribly difficult. These questions about springs, these often come up in homework problems, and sometimes they come up in exams too, because it's a great one to utilize. I remember that when I was teaching physics at the University of New South Wales, we would do something like an object would fall in free fall, then hit a spring, and then bounce back up. And there'd be multiple elements of that. You need to calculate the free fall motion, you need to calculate the compression of that spring and the force it's exerting. These are the types of questions that are more likely going to be on your exam for things relating to mechanics and forces, because we like to add different types of forces together to test your knowledge on them. So let's look at work and the conservation of energy. For an initial position of x equals 0, we know that the work is equal to minus 1/2 kx squared. For an applied force where the initial and final kinetic energies are 0, we can see that those values, it's just what we did before. It's going to be minus the opposite. So if a block that is attached to a spring is stationary before and after a displacement, then the work done on it by the applied force displacing it is the negative of the work done on it by the spring force. And again, I'm going to post a couple of really good videos offline onto the announcements page and onto the week 3 module page. So you can see some of these things in action and see some of the solutions, problems that you can solve that'll be worked out for you. So, we can look at this integral. This is just going back to the very fundamentals of calculus. The force is going to be the area underneath that curve. So, taking a one-dimensional example, we integrate the work equation, which applies for constant force over the change in position. We can show the process as an approximation of rectangular curves. So if you've got a curve, you can do little rectangles under each one of them. But if you put two rectangles together, they're just slightly off on that curve. There's a little space in there. So if you make them thinner, it's going to fill in that space. But it has to get infinitesimally small in order to fill up that entire curve. This is just going back to the basic fundamental components of calculus. So the point here, what we're getting at here, and we've shown you that work is equal to the integral of force times the displacement, or that infinitesimal displacement, dx. We can actually integrate this in all 3 dimensions. So the integral of work, that change in work is going to be the integral of the force times the distance in each of those components, x, y, and z, for a Cartesian coordinate system. So we can see that the work kinetic energy theorem still applies. Now, what about power? What is power? Power is the rate of change of work over time. So it's the time rate at which a force does work. A force does work in a certain amount of time, an increment of time. The average power due to that force is work over that change in time. The instantaneous power at a particular time is given by the differential equation. The power is equal to dW over dt, or the change in work over the change in time. The SI unit for power is a watt. This is 1 joule per second. Therefore, the work energy can be written as power times time. For example, in kilowatt hours. And when we say by power times time, all we're doing is that differential equation right here. We're just moving that time to the other side. And of course, from this, you can integrate both sides and get your derivation. So we can solve for the instantaneous power using the definition of work. So our power is equal to the change in work over the change in time. And what is a change in work? That's that force times that distance component. So force cosinified dx over dt. So work, force times distance. Well, if we write it in such a way, then dx over dt, what is that? Well, that's our velocity. So we can actually write power in terms of the force times the velocity. Now this should make sense, because remember that work is a change in position over time. It's that change in force position over time, where power is the change in work over time. Therefore, what's the change in position over time? It's velocity. So you can just think about it back in terms of our initial kinematic equations. The same principle still applies. So a block moves with uniform circular motion because a cord tied to the block is anchored at the center of a circle. Is the power due to the force in the block from the cord positive, negative, or zero? Well, it's zero, because that value of phi is 90 degrees. When you get the cosine of that, you're going to get zero. But also, if it's spinning around, it's not going to be doing that. But if it's moving outward as it's spinning, then you're going to have power. So just to summarize today, kinetic energy, the base equation is 1/2 mv squared. Work is the energy transferred to or from an object by a force. It can be positive and it can be negative. Work done by a constant force is that force times the distance. And of course, the net work is the sum of all the individual works. The work in kinetic energy theorem is that the change in kinetic energy is equal to work. The work done by a gravitational force, similarly, work G is equal to weight times that distance, or mg d cosine phi. The work done on lifting and lowering an object is simply the sum of those two components. Spring forces, so springs want to be in a relaxed state where there's no force. If you push or pull it, it exerts a force in the opposite direction. The spring constant K measures the stiffness, and the value of that spring force is minus K times that distance. So the spring force itself, for an initial position of 0, the work is minus 1/2 kx squared, and we found that simply by taking the integral. Now the work done by a variable force, so this is the integral of the force with respect to distance. Power, as we've just discussed, is the rate of change of work, so work over change in time, and the instantaneous power is given by the differential equation of power being equal to dW over dt. So the force acting on a moving object, that power is equal to force times the velocity. So we've covered a few things today in class. Go ahead and read chapter 8, specifically 8.1 to 8.5. Begin working through the problems in the back. As always, work on the conceptual problems and do as many of the word problems as you can. I will add some additional videos from different sources online to help illustrate some of these topics a bit more. I will see you next time.